Today we are going to talk about one of my absolute all-time favorite pieces of math. It's incredibly fundamental to engineering, to mathematics itself, to quantum mechanics, but it's something that has a terrible, terrible name. We call them complex numbers. And worse than that, the things that bring about complex numbers we call imaginary numbers. And before we get into any of it, what I want to do is start with kind of a poll, just to poll the audience on seeing what you guys consider to be real. What do you consider to exist when it comes to numbers? So we've already been doing a couple polls in the warm-up animations, but as a serious poll of sorts, one that's actually going to help me see where you're coming from before we begin the lesson here, I just want to ask you a very simple question. Okay, so let's go ahead and pull it up here. Pull it on up. And, for whatever reason, it seems like we're having trouble pulling this one up. Okay, there we go. Took a little delay there. Among the values 2, square root of 2, square root of -1, and infinity, which would you personally consider to really exist, whatever really existing means to you? So in theory, if you guys go to 3b1b.co/live, you should be able to answer this, and then the statistics based on your answers are going to start populating the screen. We won't know what those answers refer to. At the moment, all we know is that there's someone who has a lead, another one that's pretty close behind it, and as your answers come in and as the servers kind of digest them, we'll start to see some of the stats here. If you go to that page, by the way, 3b1b.co/live, which redirects to itempool.com, what you're going to find is at the very top, you can ask a question on Twitter. And all that's going to do is basically open up a tweet that's going to have the hashtag in it, lockdownmath. And that's the way that we're going to be doing questions through this instead of a live chat. Anytime you have a question or a comment that you want to, insert into the lesson and let that be part of the discussion, it's going to be pulled up here. And it looks like we already have one. This is from Yash Dave, who asks, if you could rename the complex numbers and the so-called imaginary numbers to something more intuitive, to a name that conveyed the fact that they have numerous applications in the real world, what would you name them? I couldn't be happier that you asked, Yash. So I have one friend who seems very passionate about the fact that we should call them sneaky numbers. Personally, I'm very fond of trying to connote spinning and rotation. And this is one of the things we'll talk about in today's lesson, is the fact that what we call complex numbers, what we call imaginary numbers, some of the main uses that they have come from very elegant descriptions of how to rotate stuff. And I hope you'll kind of see what I mean as we proceed with that. So on our poll, asking you guys which numbers you consider to really exist, which is of course a subjective question. There's no right or wrong answer here. I am genuinely curious actually how this breaks down because it's not at all a strong consensus in one direction. It seems like we've got 3 top contenders and then 3 that are falling pretty evenly behind that. So let's go ahead and take a look. What do you consider to really exist when it comes to numbers? Now, I can imagine which ones might be the top 2, but I'm very curious about the fact that there's 3 all kind of coinciding with each other there. And it looks like I'm getting a little bit of a delay before the reveal, so there's kind of this nice dramatic pause. I'll tell you, for me personally, I feel like it's very silly to answer anything that's not all of them or none of them. I can maybe understand if someone wants to treat infinity as something different because it's ill-defined. There's lots of different things that might mean. But insofar as numbers exist at all, if you consider what a number is to be a real thing, then it would, oh man, I can't believe that we're stalling out on this one. We had fixed it by live stream 2, but I guess there's going to be an oscillation between when it works and when it doesn't. But for me personally, basically, anytime that you have a numerical construct that's helpful in the real world, I consider that real. I would say that if it's something that's actually useful in an application, then it is as real as words are, right? You're never going to run into an abstract word like happiness out there, but it has a kind of reality in our minds. And things like the square root of 2, which you can't express as a fraction, or things like the square root of -1 that don't show up among real normal numbers, even if they might seem a little bit different. Oh, this is such a shame. I'm genuinely curious to see what your answers are, but it's not showing up for me, which I suppose means we'll have to move on with the lesson, but this will presumably begin working by the end and we can maybe pull things up again. So let me go ahead and take that away. What I'd like to do for you today, basically, is show you the sense in which imaginary numbers are useful, the complex numbers are useful, and from there maybe try to imbue them with a little more reality. I won't assume that you know what they are yet. It's meant to be a basic primer, but let's just dive right in, okay? The end, by the way, the very end here, I want to talk about two different trigonometric functions. And this is kind of the thing that we're going to build to, two identities from trigonometry. And I understand that maybe, these complicated identities from trigonometry is not going to be the best way to lure some people into understanding, oh yeah, complex numbers, they're really useful, you're really going to love them. But I do think it's interesting that you can have a fact that has nothing to do with complex numbers or the square root of -1. It's just trigonometry. It's everything we were talking about last time. And you can have facts that are pretty hard to remember. I remember when I was in school and we learned these addition formulas, that if you want to know the cosine of the sum of two different angles, it's this kind of long thing in terms of cosines and sines of the original two angles. There's this minus sign that would always trip people up. If you do the same for the sine, it looks similar, but there's a plus sign, and instead of having cos cos, you have cos sine. It's something that's very error prone if you're just trying to memorize it as it is. However, if you come at it with complex numbers, this is not only much less error prone, it has a very beautiful meaning, and it just falls right out. So even if you don't necessarily believe in the reality of the square root of -1, you at the very least have to admit that it's interesting that it can make other pieces of math useful, that other pieces of math a little bit more understandable too. And trigonometry is just the tip of the iceberg. If you talk to anybody who's in engineering, anybody who's going into serious math, they'll tell you that complex numbers are as real a part of their work and their life as real numbers are. But the starting point looks very strange, okay? When you start introducing this, the very first thing you do is to say, assume that there's some number I, so that I squared is equal to -1. And I think to a lot of students, there's maybe one of two possible reactions that you can have here. One is, no, there isn't, right? Anytime I square a number, even if it's negative, if I take -5, for example, and I square it, well, a negative times a negative is a positive, so I get 25. Any number that you square, if it's positive, well, that just stays positive. So it seems like no matter what, when I'm squaring numbers, I always get a positive number. I'm never going to get anything negative. So this does not exist, no such number. However, if a mathematician comes and says, oh, no, it exists, we've defined it so that that's the case. I think the other reaction someone can have is, hang on a second, you can do that? When you have a problem that you can't solve, you can just say, oh, I've defined things so that we now magically have a solution. Okay, next time I'm having trouble with my homework and I don't know what the answer to x is, I will be like, let x be the value defined to be the answer to this question. So if you're uncomfortable with this, you're definitely not alone. In fact, René Descartes coined the term imaginary for these numbers as a derogatory. It was meant to make fun of the fact that obviously there is no such answer and it shouldn't be taken as serious math. And then we stuck with that as a convention and we still call them imaginary numbers, which is genuinely absurd. But that's not the only weird assumption that we make. The second weird thing that you do when you start talking about complex numbers is to say, there's not just such a number I, but we're going to give it a home. Instead of the real number line, which, all of these numbers we know when we square them, you can't get a negative, what we do is say I lives in a different dimension. I lives perpendicularly. There's one above, and then there's one below, -I, and you can have -2i. You scale it however you want. Essentially, it's proposing that numbers be two-dimensional and that I has a very specific home, 1 unit perpendicularly above the real number line. And okay, if we want to extend our number system, I get it. Maybe it's useful to put some kind of number up there. But why I, right? Why not say infinity is the number that sits 1 unit above 0, or 1 divided by 0, or any other problem that you couldn't solve before and you make up an answer to? Why should that live there? What on earth does the idea of a point 1 unit above the real number line in a separate dimension have to do with squaring to -1? So I hope to answer this for you. At the very beginning, let's just talk about how if you're adding numbers that are two-dimensional like this, the rules are pretty straightforward and it operates essentially the same as vectors, for any of you who might be familiar with vectors. So let's say, hypothetically, I have a number, I don't know, let me draw one here that's going to be 4 plus I. Okay? And then I'm going to take a second number, and it's helpful to draw them as vectors, kind of an arrow from the number 0. And this one is going to end up at -2 plus 2i. So what I'm saying is you take the real number -2, and then you move in that perpendicular direction into the extension of our number system, which again, you're kind of asking the students to take a lot on faith here that you're okay to do that you're allowed to just pretend that the numbers extend in this direction. If you take that on faith and you follow, hopefully the fact that it becomes useful helps to justify why we're doing any of this. So my question for you is simply, what happens when we add these two numbers? Now, assuming that our question system has not broken down, I should be able to do this as a proper poll. And let me go ahead, I guess we can first check the previous poll. Okay, things seem to be working. So we can take a little step back in the lesson. So I'm just genuinely curious. I want to know how you guys answered on this one. It looks like there's a back and forth between answers F and D. So F is all of them, saying that all of these should be considered real. And interesting, D is the one that says you should consider 2, square root of 2, and -1, but not infinity. So there's a good contingent of you out there who would just reject infinity as being considered real, but are very comfortable with the square root of -1. That's awesome. And then after that, it looks like C, people who reject the square root of -1. Fascinating. I actually would have thought that none of them would have come higher than that. None of them is much lower at A. Okay, so it looks like we've got a cohort of people who are comfortable with -1, a large cohort are uncomfortable with infinity. That's a topic for another day, don't worry about it. And then a number of people who are kind of in that middle ground of maybe not being super comfortable with the idea that -1 might be real. Let's see if we can convince you of the difference of that. So for our first much more mathematical question, as kind of a warm-up, I just want to ask you to add these two. Before I've taught you how to add them, make a guess at how it might work, and I hope that it feels pretty straightforward. Addition is actually the least interesting part of this, but it's a good thing to know when you're learning about complex numbers. It's definitely one of those operations that you are going to need to know. Unfortunately, and you can tell by the fact that I'm stalling in what I'm saying here, it looks like the question is still not loading completely correctly. So I'm going to have a stern word with Cam and Eater behind the scenes, who have otherwise built such a beautiful, beautiful interface that's helpful for this kind of back and forth between you guys and me. I'm going to have a stern word with them behind the scenes. But in the meantime, let's go ahead and move forward with the lesson here. So I guess I can pull it up on the just on the piece of paper, and you can follow along at home, see what the addition might be. It turns out to be relatively straightforward. If you're moving 4 units to the right and then 1 unit up, and you want to add the idea of moving 2 units to the left and then 2 units up, well, you just do each of those one at a time. I'll go ahead and pull out black here. The real part is going to be those 4 to the right, then -2 to the left. Okay, straightforward enough. And then the imaginary part is going to be this 1 unit up, and then these 2 units up, 1 plus 2, times I. So is that 1i plus 2i. And then when you work that out, 4 minus 2 is 2, 1 plus 2 is 3. A nice simple introduction here. Addition doesn't really have anything complicated going on, which is great. That means that it's one fewer thing for us to worry about. What is so complex about complex numbers after all? Well, where everything becomes interesting is when you try to multiply these numbers together. So with vectors, there's not really any notion of multiplying them to get 2 vectors back, at least when we're in the 2D plane. You have some notions like cross products and dot products that in 3 dimensions can get you something like it. But the rules end up being very different from that in the number system. You can't really do algebra. You can't do things like assume that if 2 numbers multiply to make 0, then one of them has to be 0. But complex numbers are going to end up behaving much like the real numbers, so rules from algebra can carry over. But to understand what that rotation rule is, oh no, I'm giving things away, what that multiplication rule is, I just want to ask you a simple question, which is basically, suppose I have the point 3, 2, okay? We're not even going to think of it as a complex number per se. If I just have some sort of coordinate grid, and I go to the point with x-coordinate 3 and y-coordinate 2, what is the 90-degree rotation of this? If I rotate it 90 degrees, and let's say counterclockwise. Geez, writing is difficult. Counterclockwise. Okay. Now, what's lovely about this is we can basically just turn our paper to figure it out. We say, okay, if it started at 3, 2, and then I rotate 90 degrees counterclockwise, I can just read that off now as being -2 in the x direction, and then 3 in the y direction, if I had rotated the whole plane like that. So what we've done here is we've taken 3, 2, and then we convert it to -2 3. Something which maybe in our original system, it looks like this, -2 and then 3. That's going to be the 90-degree rotation. And what's nice here is that that rule is very simple and it applies to any pair that we might have. If I took a pair of numbers a comma b, okay, and then I said, where's that going to rotate to if I rotate it 90 degrees? It's going to end up by swapping the coordinates, b, a, and then making that first one negative. That's a 90-degree rotation. And a nice gut check here is to say what happens when we do that twice. What if we do that same very mechanistic operation again twice? And I'm going to go and take this, I swap the two coordinates, we get a, negative b, but then that first one becomes negative. So that was another 90-degree rotation. Well, what's happened here is we've just made both of the coordinates negative. And that's reassuring, because if I take some point sitting at AB, and then I rotate it 90 degrees, so this will be my initial 90-degree rotation, and then another 90 degrees, that's the same as a 180-degree rotation. Oh, no, I've done that wrong. That will be the same as a 180-degree rotation, which should look like this. Ignore the other vector that I drew, which is just taking both of the coordinates and making them negative. Negative a, negative b. Okay? So that's reassuring. This operation that does a 90-degree rotation actually behaves like you would expect it to. Now, why am I asking you this? Well, I'm being told that supposedly I'm allowed to ask you questions again. So I'm going to have you do your very first complex product. Oh, look, a lot of people did submit answers. Very good. Great. Let's grade the complex addition, actually. Let's see if it is as straightforward a process as I was hoping it was, and see how much explanation is demanded. Okay, so it looks like a majority of you did get the correct answer, which is 2 plus 3i. Very good, very good. 52 of you answered simply 2, which would have been the real part of the answer, so maybe just the fact that there's some vertical component and you need to still add those vertical components. Or maybe those of you who answered 2 reject the reality of imaginary numbers, so you just don't even acknowledge that vertical component. Some of you answered -2, 3, which I guess is just making, that's just swapping up whether you're taking 4 minus 2 or 2 minus 4, so that's completely understandable. We've got 2 plus 3, which is maybe just dropping off the I. So I think maybe a lot of like simple errors in entry, and that happens to all of us, especially on tests, is sometimes you know what the right answer is, but then you forget a symbol or you swap two. So that's all very good. Let's go ahead and try our very first product, though, like I said. So here, because I already talked through one of the questions, we're going to go ahead and skip ahead of it. We know how to rotate something like 3 comma 2. So I'm not even going to give you time to do that and properly grade it. Stall, words. They tell me that it's working, and yet it's very slow for me to progress forward. So, if I'm not going to have a stern word with them, you guys can go at them on Twitter too, under the same place that we ask questions, and just say, hey, Cam and Eater, can't you make the live questions work a little bit better for us? Okay, I think we're finally there. Everybody ready? Aha! Wonderful. Very simple question. I want you to take the number I, and I want you to multiply it by 3 plus 2i. And even though I haven't really talked about the rules for multiplication, what I can say is pretend like it operates just like it does for normal numbers. You've got things like the distributive property, where you can distribute this throughout. And then the defining feature of I is this idea that I squared is -1. That's the only special thing you need to know about that. Other than that, just treat it like it's a normal number, okay? And then proceed forward with the product. Wonderful. Okay, so it looks like we've got quite a few of you coming in to answer, which is always lovely. Super exciting for me, by the way, just how many people are enthusiastic about coming and like getting back to the fundamentals of math in this lockdown, and just, we're going to sit back for an hour and we're going to learn about complex numbers, and we're actually going to participate. We're actually going to answer questions as you do it, rather than sitting and passively watching. This is genuinely delightful to me. Okay, this isn't necessarily a question I was expecting to divide the audience necessarily. So unsurprisingly, it looks like we have a very strong majority in one direction, hopefully in the correct direction. But if not, that would heavily inform where the lesson should go. So that would be quite useful. And I think that's probably enough time. So I'm going to go ahead and lock the answers into this one. Okay. And it looks like the majority of you answered -2 plus 3i. Which is absolutely correct, absolutely correct. So there's two ways to think about this, okay? One of them is to walk forward with the algebra and just do it a little bit mechanistically. Okay, so if we pull ourselves up our sheet, if we take I times 3 plus 2i, it just distributes. I times 3 is going to be 3i. I times 2i is going to be 2 times I squared. By definition, I squared is negative 1, which means that our final answer is going to look like negative 2 plus 3i. Okay, and like I said, it looks like a majority of you correctly did that product. Now, it's one thing to just walk through it mechanistically. It's another to step back and say, what just happened geometrically, right? Because what we just talked through was the fact that if you want to rotate numbers 90 degrees, the rule is to swap the two coordinates and then multiply that first one by negative 2. Well, look at what's happened here. We've got 3 and 2. Those coordinates have been swapped. 2 is now the real part, 3 is the imaginary part, but that 2 got multiplied by a negative 1 because I has this defining feature of squaring to become negative 1. So that should give you some indication that, okay, multiplying by I has this action of rotating things by 90 degrees. Maybe that means that it's not a crazy thing to do to geometrically position I at a 90-degree angle with the real number line, okay? Now, to really see why that ends up being useful, it turns out that if you have a number that behaves this way, it gives you a computational mechanism for all of the other types of rotations that you might want to do that might not necessarily be 90 degrees. And to show you why this works, I'm going to go ahead and pull up an animation. So let's say we have any number z, and in this case, z is going to be, let's see, where do I have it? Z is going to be at 2 plus I. Great. And let's say I want to understand what does multiplying by z do to every other possible complex number? Well, we can go one by one. The very first one, that's relatively simple, is if I ask, what is z times 1? Where does it take the number 1? Well, z times 1 is going to be z. So we're going to take the number 1, which I might draw with a little yellow arrow, and we're going to rotate and stretch that arrow up to the point where z is. Great. A kind of trivial fact. Even though it's trivial, I'm actually going to take a moment to write that down, just so that we can, oh, no. That's for later. That is Randy. Don't you guys worry about him. He'll be coming in just a moment. So I just want to write down 3 crucial facts that are going to influence rotation. 3 facts. I'll call it 3 facts about multiplication. The first 2 are going to look simple. The third one is going to look innocuous, but it ends up being extremely constraining. So the first one is that if I have any number z and I multiply it by 1, will I get the number z back? Okay? Geometrically, that means we stretch and rotate that vector 1 to get what we want. The second one is that if I take z times I, from what we just talked about, that is the 90-degree rotation. What I might write is like, rotate by 90 degrees the number z. Okay? So off in our animation, what does that look like? Let's see, we've already multiplied by 1. We take I, and then it's going to move to whatever the 90-degree rotation point for z itself is. Okay? So, 2 down, infinitely many to go. Okay? And we know what it does to 1, we know what it does to I. Let's see if we can understand what z does to any other possible number. Well, it turns out those 2 is really all we need to work with if we have the distributive property. So the third fact that's going to look kind of innocuous is, let's say I take this z and I multiply it by c plus d times I, where c and d are just any 2 numbers. Okay? Well, this is going to distribute, so z times c, I'm actually going to write that a little differently. I'm going to write it as c times z plus z times di, which again I'm going to write in kind of a funny order and write that as d times zi. Now the idea here is, well, we know where z is, we also know where z times I is, so if we're just scaling them up by some other constants, that completely constrains where we need to go. So let me go ahead and write this down with an example, okay? Let's say that we go back here and I want to know what multiplying by z does to anything. I want to convince you that it rotates all of the grid in a way that keeps these lines parallel, it keeps them evenly spaced, keeps them perpendicular to each other. It applies this very constrained rule to the whole plane. And really just think through any one particular point for this. Let's say that we have 2 times negative I. Okay, so you move 2 units in the positive right direction, and then -1 unit in the vertical direction. Well, after the product, where that's going to land has to be 2 times wherever z lands, plus -1 times wherever I lands. Okay, and we see that, right? It's 2 times this yellow vector, and it'll be -1 times the green vector. So here, even before you actually work out the product, we could just read off the fact that z, here which looks like it's 2 plus I, multiplied by 2 minus I, must land on the number 5, okay? So I actually want you guys to work this out algebraically because I do think that it's edifying to see this work in practice, right? The fact that we have this geometric rule where we're just kind of stretching and rotating, and this corresponds to an otherwise very mechanistic process of expanding out a sum. So let's pull back our quiz, and I'm going to... It's a little bit silly because I've revealed the answer, but what I actually want you guys to do here is take a look at the question which says, what is 2 plus I times 2 minus I? And if you have notes right now, if you have a pencil and paper, which I encourage you to always come to class with, I want you to try working it out. Do the first inside, outside, last distribution property, just to see mechanistically what number ends up popping out from this. And then we'll try to see how that squares with the geometric intuition. So while you're doing that, while you're working that out, hopefully on pencil and paper, it looks like we've got a question from the audience, which is I the same as I and j the vectors in physics? Great question. Actually, that's a much more interesting question than you might think it is. The short answer is no. So in physics, you often describe the rightward direction as I, and then the up and down direction as, so we got another one here. Let me finish answering the question first. So in physics, you often have this situation where instead of describing the xy plane, you describe the right vector as I, sometimes I hat, and the vertical one as j hat. So that's a separate thing. That's how physicists will describe the right direction and up direction for vectors. They're not necessarily describing complex numbers, totally separate thing. What's more interesting, actually, is that the reason that convention came about, I believe, has to do with a number system that extends even beyond complex numbers. It's called the quaternions. So with the complex numbers, we introduce something called I. With the quaternions, we introduce j and k, these two other numbers, both of which also have squares to -1, as it happens. And the guy who invented them, Hamilton, he was trying to describe three-dimensional space very elegantly. And using the purely imaginary directions, I, j, and k, became a nice way to do that. And I think it's because of that and his attempts to push that forward that the conventions slipped into normal physics to just describe those as I and j. Of course, that leads to serious confusion now, because if we look at how physicists think of things, you know, I is in the right direction, j is in the vertical direction, but with complex numbers, I is, of course, in the vertical direction. So it just makes for a whole potential mess. Now, what was our other... Oh, no, it looks like they took away the comment. Oh, man, there was a comment giving them some sass, and then they got embarrassed, so they pulled it away. Well, it's on screen. It's in there for everyone in the future to see. And I think that's probably been enough time to work through our little bit of algebra here. So let's go ahead and grade it for everyone to see. And it looks like the vast majority of you... Well, I told you the answer, so I'm going to assume the vast majority of you are giving the correct answer. Oh, interesting. Okay. So it looks like 5 is correct, and that's the most common answer. But then the ones where it missed were 3 and 4. And maybe we can try to understand why 3 and 4 would have been common misconceptions on this one. 69 is close. 0i plus 5 is correct, but I guess just formatted in a weird way. So let's go ahead and work this one out by hand, okay? It's actually, you know, kind of a pleasant process to multiply complex numbers because it's so deterministic. You know what you have to do, you know where you start, you know where you're going to end, and it's really just kind of practicing through it. So 2 times 2, that's the first thing that we get. And then you take the inside parts, I times 2, so that's going to be 2i. And then the outside parts, which is -i times 2, so that's -2i. And then the last part, which is I times -i. So that'll be -i squared. The defining feature, remember, is that I squared is the same as -1, which means that the real component of our answer is going to be 2 times 2, or 4, now minus -1, which is plus 1, so that'll be 5. And then the imaginary parts cancel each other out. That 2i cancels out with the -2i. So to everyone on the quiz who answered 5 plus 0i, extra credit to you, because that actually is 100% correct. You're even emphasizing that we're doing this in a complex context, so there's no reason that you should have been graded incorrectly on that one. However, what's interesting here, those of you who watched the very first lecture might notice the similarity with difference of squares, and this is effectively a difference of squares type question. And I'm going to guess that those of you who answered 3 or 4, it probably came down to, if you answered 3, it would have been because you took this 4 and you subtracted 1, rather than subtracting -1. Very common mistake, no harm in that. And then if you answered 4, it comes from forgetting the fact that I squared can be simplified into a real number. So that, that very much counts for the real component of your final answer. Now, what's interesting, I think, is that process of just walking through the algebra feels very different from this geometric idea that we had before of saying multiplying by z has the action of rotating and stretching things. And how it rotates and stretches things is in the way that's necessary to get the number 1 to sit on the number z. And in fact, I have a good friend, Ben Sparks, who is a frequent number file contributor, some of you might recognize. And I asked him to whip up a little GeoGebra thing because he's just a GeoGebra whiz. And he actually created basically the complex number equivalent of a slide rule that we can play with here. So the way that this is going to work is that I can take the number 1 and sort of drag it around the plane. And as I do, the rest of the grid moves in the way that it has to, so that the origin stays fixed in place, and then everything else kind of stays rigid with the exception of being able to stretch. So the way that you might use this is to say, let's say we want to know what z times w is. Well, I'm going to stretch and rotate the number 1 so that it lands on z, and then I'm going to follow what happens to w, which is now drawn as a orange vector. Follow what happens to w, and as it lands there, we can just read off that it ends up at 5. Now, even though in practice computationally you would be working it out with the algebra like we just showed, having in the back of your mind that this is how they operate helps draw the connection between complex numbers and geometry, and also trigonometry, which we'll get to in a moment. And that turns out to be a much more helpful connection than you might expect. So let me go ahead and ask you guys a second question here, which is, bring back our helpful little friendly quiz. Given what I just told you about how complex numbers act, I want you to guess for me. It's okay if you don't know. It's okay if you just want to hazard a guess here. What is the complex number z so that multiplying by z has the effect of rotating 30 degrees, or pi/6 radians counterclockwise? Okay? So you want a number z so that when it's being applied as an action, and you're saying, what do you do to all the other possible complex numbers? The corresponding action is to rotate by pi/6 radians, or 30 degrees. Okay, great. We've got a lot of answers coming in. Strong consensus around one of them, which is always a good sign. Let me show you how I might draw this out if I were doing things. So I would take a look at a unit circle of some kind, and luckily I have my infinite supply of unit circles sitting right here. And I would say, okay, I know that the action that I want is going to be whatever takes the number 1 to something that's the 30-degree rotation of the number 1 that sits up here. Whatever complex number z this is going to have the appropriate action. And then from there, it's all of the trigonometry that you and I were working through last time. So let's look at our answers and let's go ahead and lock them into place now before we talk through the explanation. And the correct answer in this context is D, which is cosine of pi/6 plus I sine of pi/6. Congratulations to the majority of you who correctly answered that. Very interesting to me, actually, is that the second most common answer was A, which is 1 plus pi/6. And I think that's an utterly reasonable guess, actually. And let's take a look at why. So if we go back to our friendly unit circle, the number we were going for is, like I said, sitting pi/6 radians around. And from everything we talked about last time, the x component of that is the cosine of pi/6. This is sort of how cosine is defined. And then the y component of that is going to be sine of pi/6. Which means that that number z that we're dealing with, okay, is going to have an x component of cosine of pi/6, and then an imaginary component, what's in the y direction, of sine of pi/6. Great. Now, that second most common answer, like I said, that's very interesting. If we pull it up, it was A, which was 1 plus pi 6 over I. Let's take a look at where that sits. I'll bring in a second cleaner unit circle here. Like I said, I've got an infinite supply. They were guessing that it's 1, and that instead of walking pi 6 around, that you walk just straight up pi 6. Okay? Which is actually quite close, right? Especially for small angles, if you're just walking straight up, that's not too different from walking around the circle. So if you were to try to use that number to have the action of rotating by 30 degrees, it would have an action of rotating by something that's slightly less than 30 degrees, and then it would stretch things out by something that's slightly more than a factor of 1. But it's actually close, which is cool, because usually the misconceptions might be like very wrong computationally, but the idea that the misconception here was like computationally quite close indicates that maybe the geometric reasoning was lining up with truth, which I think is awesome. So to give you an illustration of how this might actually be used, okay, we have a number that has this action of a 30-degree rotation. I want to bring in, of course, a friendly pi creature for us to all think about. Randy. So let's say that I have a pi creature and I'm, I don't know, animating a video, and at some point, for whatever reason, I want that pi creature to rotate 30 degrees. Okay, I just want him to rotate. There's lots of ways you could do this. One of the most common ones in computer graphics is to use matrices, which might be a whole topic for another day. But a tactic you could use is to use complex numbers. And the way this would work is to think of our pi creature as living in the complex plane. And then in any kind of computer graphics, it's always defined with various points, often these control points around it. And each one of those control points I would give complex coordinates to. So for example, let's say the lower right foot here, or I guess stage left, our right, looks like it has coordinates about 1, -3. So that would be given the number 1 minus 3i. And then from what you guys just told me in answering the question, if we want to take that point and then figure out where it gets when we rotate 30 degrees about the origin, what I should be multiplying it by is cosine of 30 degrees by sine of 30 degrees. And if ever you wanted to be convinced that complex numbers are just as real numbers, I think one factor to consider is that many programming languages have built into them complex numbers. They are considered as real numbers. So what I might do, I could pull up a little Python terminal for us to play with. And complex numbers, if I write something like 3, -1, are considered a valid type. In this case, they use j. I think basically because in programming parlance, I is often used as an indexing variable, so they just go with j instead. That actually matches with electrical engineering convention too, where they, instead of using I for the imaginary number, they use j, because again, I was kind of already used. So 3 minus 1j, you can just read that as being the same as 3 minus 1i. And I could take this number and I can multiply it by other complex values. I don't know, like 5, 4, 2. If I multiply that, it's going to apply the rules of complex multiplication, which basically is just foiling it out. You can think of this as being the real part is 3 times 4, or 12, minus -1 times 2, because remember that I squared gives us that negative, so that's where the 14 comes from. And then the imaginary part is going to be that -1 times 4, which is -4, plus 3 times 2, which indeed works out to 2. So that's kind of cool. Python seems to be working all of this out for us. And what that means, remember, is let's say that we wanted to rotate our pi creature, and let's say I'm just going to focus on one point, like his foot sitting here, which is at 1, -3. So let's say I define the foot to be sitting at real part 1, imaginary part -3. The rotating number that I want, z, is what you guys figured out for me. We're going to need a little math for this, so let's import math. Always a sign that you're about to have some fun. So we're going to call z a complex number whose real part is the cosine. Well, I can't write 30 degrees because this will all be in radians, so I'll write it as pi 6. That's the same thing as 30 degrees. And then the y is going to be the sine of that. Sine of math.pi over 6. Great. So if we look at its components, the real part is around 0.866, and the imaginary part should be exactly 1/2, but often you get a little numerical error because computers, they can't get all the real numbers perfectly. There's just not enough information in the universe. So they have to have a little bit of an error there. Some of you might recognize that that first part is the square root of 3 divided by 2. This is everything we were working out last lecture for computing things like the cosine of pi 6. Now what this means for us is if we take z times foot, right? Where remember foot was that 1, -3. Z times foot should tell us where it goes. When you just go through the mechanistic operation of complex multiplication, this point should tell us where it lands. Evidently, it's supposed to land at around 2.3 as a real part, and then -2.09 as the imaginary part. And indeed, when we play that out and we follow our little foot point here, where does it land? All right, it looks like the real part is a little above 2, and the imaginary part is a little less than -2. And any deviation there is probably because the foot wasn't exactly at that point 1, -3, like I said. But you can see what I mean. In principle, you tell the computer to do this for every single point in a given image that you want, and it will tell you where the outputs should be. It'll tell you where the rotated versions should be. So complex numbers are certainly as real numbers in that respect. It looks like we've got a question from the audience, so let's go ahead and pull that up. Seal Programmer asks, what is the biggest reason that people use vectors and matrices to represent rotation instead of complex numbers? That is actually a very interesting question. I don't know if there's a great reason, actually, because if all you're going to do is rotate and then potentially scale things, you could have everything defined in terms of complex numbers in 2D graphics. In 3D graphics, that actually wouldn't work. Complex numbers only describe rotations in 2 dimensions. However, if you want to use a number system to describe rotations in 3 dimensions, instead of using matrices, you could use these things called quaternions, they're basically the complex numbers on steroids. And in fact, they expose you to fewer errors. Like there's errors that come about when you try to use matrices for 3D rotation. This thing called gimbal lock. Talk to any roboticist or any computer graphics programmers. They'll tell you that gimbal lock is a real pain. And the quaternions, this sort of complex numbers on steroids, helps to solve that problem. There's a whole other contingent of people who feel passionate about something called geometric algebra. That is a whole other topic, potentially for another day. But that's a really valid question. You've got these 2 perspectives on one possible operation. But if we're just coming at it from the idea that complex numbers play a role in other parts of math and in other parts of engineering, I think thinking of the rotation implications really helps us see that. And this is particularly visceral for me when I think in terms of trig identities. So if you remember at the very beginning, I opened up by talking about one particular trig identity, and without pulling it up again, I don't want to go back and just read off of it. I'm going to ask you one more question, which this is going to be a tricky question. This one will actually take some time to work through, which is I want you to calculate for me the cosine of 75 degrees, okay? And let's go ahead and pull this up as a quiz question. So let's pull up our quiz. Let's move on to the next question. Let's cross our fingers and hope that Cam and Eder have not broken anything again. And that's all it's asking. What is the cosine of 75 degrees? Okay. Now let me get you started here on how you might think about it. 75 degrees, it's not going to be based on any triangles that we might have seen. Maybe you've seen a 75-degree triangle and you happen to remember what its side lengths were, but most people won't have. However, what you can do is note that 75 is the same as taking 45 degrees and then walking another 30 degrees around. Okay, 45 plus 30 degrees. And if our question is asking us for the cosine of 75, one way to think of it is if you first walk 45 degrees around and then you walk another 30 degrees around, what is the x-coordinate of that corresponding point? Okay, so this is going to have some coordinates x, y. The cosine of 75 degrees is asking for the x-coordinate of that. Now, like I said, I think this is not easy. Okay, so it's going to take some time to work out. And while you guys are working this out, I want you to actually pull out some pencil and paper and think it through. I'm just going to pull up a little pause and ponder music and give us, I don't know, I might give us a full 60 seconds or so to like noodle this one out and think it through. And in the meantime, if you want to ask any questions, you know how to do so through Twitter. It's with the hashtag #LockdownMath. And I might go ahead and take a couple questions while people try working this out by hand, which, again, I heavily encourage you to do. Even if you're not watching this live, even if you're watching this at a later date, this is the time to say, okay, I'm going to pull out my paper, I'm going to try to think this through. And now I'll stop talking, I'll let you just think. Certainly don't feel rushed, by the way. Even if there are some answers rolling in right now, That is by no means any indication that you should have finished or anything like that. So interestingly, we do have a strong lead, but it's not at all a strong second place. So it seems like the way that assuming that the lead is correct, the way that the errors have happened is not in a consistent way, which is interesting, and that'll be fun to dissect once we reveal what the answers are. Let me check if there's any new questions that have rolled in. No. Which suggests to me that the two folks that I have behind the scenes who are supposed to feed me questions are probably desperately wrangling with something item pool related. Those of you who have already submitted an answer, or who think you already know the answer, by the way, I want you to take a moment to seriously guess what you think the second most common answer is going to be, and where exactly the misconception could have taken place. Or to double check your work. You very well might be one of those sitting in the misconception territory, which, you know, it's a lot to work out. There's a lot of different failure points along the way. All right, so with that, I'm going to go ahead and lock in the answers. And if you wanted to still work it through, even if the answer isn't going to be recorded, that's totally fine. We're going to walk through it in a moment. But I'm going to lock them in just so that we can see what the correct answer turns out to be. And the correct answer is D, which it looks like a majority of you got, so that's awesome. The second most common was C, which really only differs by a minus sign. And I can actually guess why that's true already, so that's interesting. After that is B, where there's a square root of 3 instead of a square root of 2. Okay, so we actually have a pretty good distribution on this. I think that this shows that this is not at all an obvious question and can take a little bit of noodling to figure out. So if I saw this on a test, okay, let's say that someone threw like a high school math test at me right now, and it said cosine of 75, you know, I would know that in principle I'm supposed to be thinking of this as in terms of friendlier angles. I know that 45 degrees is a friendly angle for trigonometry, and I know that 30 degrees is. What I don't have memorized, though, are the addition formulas. I learned them once, slipped out of my head, definitely don't have them memorized, but I do know how to rederive them on the fly. Basically, the idea is that we take the complex number associated with the 45-degree rotation, which is going to be cosine of 45 degrees plus I times the sine of 45 degrees. I take that complex number, and I'm going to rotate the complex number corresponding to a 30-degree rotation. So I might even just pull up yet another unit circle here and say the one that sits 30 degrees away, I want to multiply it by this number. Well, what is that number? Its x component is the cosine of that. So the real component is the cosine of 30 degrees. And then the imaginary component, okay, the vertical component here, is the sine of 30 degrees, which looks like it's, you know, the smaller leg of a 30, 60, 90 triangle, which is going to be 1/2, but we'll work out the numbers in just a moment. Sine of 30 degrees times I. And by the magic of complex multiplication, which I hope isn't magical based on what we walked through a little bit earlier, the effect that this will have is to rotate by one and then rotate by the other. So what are these values? Cosine of 45 degrees is the square root of 2 divided by 2. Sine of 45 degrees is the square root of 2 divided by 2. And if you don't remember that and you want to work it out, the way to think about it is that a 45-degree angle is going to create an isosceles right triangle. So if we don't know what this side length is, we at least know that it's the same as the other side length. So if the hypotenuse is 1, we know that x squared plus x squared is supposed to equal 1. That's the Pythagorean theorem. that tells us that 2x squared equals 1. So x squared is the square root of 1/2. And then that's actually the same as writing the square root of 2 divided by 2. You could also write it as 1 divided by the square root of 2 if you want, but these are equivalent forms. So if you forget, you just draw the triangle. It's no big deal. Cosine of 30 degrees. Well, if we have our 30, 60, 90 triangle, the long side of that, from everything we talked through in the last lecture, is square root of 3 over 2. Square root of 3 over 2. And then the sine of 30 degrees is 1/2. And now we just carry out the complex product. It's not exactly a fun prospect, maybe, but it's really just 4 operations, so it's not going to be too bad. The real part is going to be our cosine times our cosine. Okay, so that's going to end up being our square root of 2 over 2 multiplied by square root of 3 over 2. Okay. I'm also going to package in when we multiply both imaginary parts. Okay, I guess I was a little inconsistent. I wrote I times sine and then sine times I, but it's the same thing. So I'm going to include that square root of 2 over 2 multiplied by the 1/2. But because each of them has an I, we also multiply it by I squared, which by definition is -1. So we get this negative sign in here. And that's going to be the real part. Okay, which is actually all we need. We just need the real part, and that gives us the x coordinate of the, where did I drop before? Here we go. If we rotate 45 degrees, then we rotate another 30. The x component of that, the real part, is going to be the final answer. So we'll do the sine part in a moment too when we make it more general. But just for the sake of answering the question, this ends up being root 2 times root 3, which is root 6 divided by 2 times 2. So root 6 over 4 minus, and that minus sign came about because of the I squared, minus square root of 2 over 4. Okay, so all in all, that ends up being root 6 minus root 2 divided by 4. And if we pull up the question, I think it's very interesting that the second most common answer, the most common mistake, you might say, is only different because of that plus sign. And if we look at the math, where that came from, as it happens, is the idea that this was a minus sign, which came about from the idea that there was an I sitting in front of each sign. So the most common misconception came from maybe forgetting to apply the fact that I squared is equal to -1. At least if you were going about it using complex numbers, which from the whole context of the lecture, of course we want to. So this actually corresponds to a much more general formula. And I think it's edifying to write out that general formula for ourselves. Because anytime that I've forgotten what the sum of two angles in trigonometry should be, it's totally okay because you can rederive it relatively quickly if you're comfortable with complex multiplication. And the more math that you do, because it shows up all over the place, you actually get very comfortable with complex multiplication, even if you, like me, become very rusty on things like trigonometric identities. But with that comfort, you can very quickly rederive what the angles should be, or what the some identities should be. Sine of beta, writing and talking at the same time. So remember, the way to think about this is that this first number is what we get by finding a complex number that's basically just rotating alpha around the unit circle. If you rotate an angle of alpha around, that's what this first number is. The second number tells us what you would get if you rotate an angle beta around. So let's say there's some other angle, which I might write down here. The whole angle from the x-axis would be, how should I write it? I'll write it as beta. That doesn't really connote that it's the full angle. Just bring I'll just do it as a separate friend over here. Beta. So I think, like, when I see these terms, cosine alpha plus I sine alpha, I think in my head very visually of a point on the unit circle in the complex plane. Similarly, I think of a point on the unit circle in the complex plane. And I know that multiplying them together means that the action of one of them is rotating the other. So the final result we know is going to be the point that sits alpha plus beta around. Alpha plus beta plus I times the sine of alpha plus beta. Wonderful. But on the other hand, if you go through the mechanistic FOIL operation, you will get an alternate expression for the answer. And by having an alternate expression, you have an identity, which I think is pretty cool. It's a sign that when you have a non-obvious relationship, like the algebra of complex multiplication and the geometry of complex multiplication, you can leverage that non-obvious relationship to get yourself real identities. Okay, so how does this work? The real part is going to consist of multiplying those cosines. So we have cosine alpha times cosine of beta. And then it also consists of the two imaginary parts multiplied together, because that I squared becomes real. I times sine, that's it, I won't write anything here. It'll be that sine of alpha, and then the sine of beta. And because we have an I squared, we can consider that a negative one. Okay, so it's cosine alpha, cosine beta, minus, I sort of accidentally started writing a plus, so we're just going to live with that, minus sine of alpha plus sine of beta. Sine of alpha times sine of beta. Okay. Obviously, it's a lot of algebra, but it is satisfying the idea that you don't need to memorize this. And again, when you do this regularly, when you do complex multiplication regularly, you can kind of see this pop out where you're like, oh yeah, it's the two real parts minus the two imaginary parts. That, as a pattern, is something you start to recognize. And that when you want the imaginary part of the product, that you take the other two, like in this case, it's going to be I times sine times cosine. So the sine of alpha times the cosine of beta, plus the cosine of alpha times the sine of beta, the cosine of alpha times the sine of beta, long complicated formula, all of that times I. This long complicated formula is giving you the angle and sum identities. And sometimes you can write this out in a much more compact form. This is not a commonly used notation, and I'll explain why in a moment, but sometimes cosine plus I sine of something comes about commonly enough. It has this meaning on the unit circle that it's written as CIS, okay? In this case, CIS of alpha. So everything that we just wrote down could be written more compactly as CIS of alpha times CIS of beta is equal to CIS of alpha plus beta, okay? This is communicating the very non-trivial fact that complex multiplication lets us work out rotations in the way that we want to. Again, that's not standard notation, and I'll explain why. There's a much more standard way to write these, but it's weird, so I don't want to just kind of throw it down there. But before we do that, I want to illustrate how you can do a little bit of magic when you have this proper intuition for complex numbers and how they multiply. So let me pull up our quiz again, and let's move on to another question. And this question asks, which of the following values of z satisfies z squared equals I? Okay, so there's two ways that you can think about this. I'll talk about them both. And I'm just going to give you a moment to kind of think this one through. And while you work that out, let me go ahead and take a question from the audience. Ahmed Osama asks, what is an application that is impossible to achieve without complex numbers? Convince me that they are needed. They're fun to work with, maybe, but they made things easier, but can we do without them? I would say, I believe, yeah, you can absolutely work without them, because you can basically use rotation matrices in place of complex numbers. So what's nice about complex numbers is that when you're adding things and when you're multiplying things, you're dealing with the same type. They're both complex numbers. But if you wanted to describe this all with matrices and vectors and such, when you're adding stuff, you'd be adding vectors. But then when you want to do rotation type actions and stretching type actions, you'd be transferring to instead dealing with matrices. So that's fine. You just have to keep that jumbled and use them differently. I'd be willing to bet pretty much anything you can do with complex numbers, you could do there. It'll become much less elegant, and I guess one of the main things that would be just really awkward is the fundamental theorem of algebra, which we'll talk about in a moment. But it basically says anytime you have a polynomial of degree n, so the highest term you see is something like x to the n, among the complex numbers, it has n different solutions. So that's very elegant. It's very nice to work with. It definitely makes the lives easier of anyone who's working with things where polynomials come about, to include matrices and things like, I don't want to throw around terminology, but when you're computing eigenvalues and such, you find yourself with polynomials, often of high degree, and it's nice to have solutions to them. I can conceive of constructing some kind of way to work with the numbers where you have like solutions to all of these, where the solutions are expressed in terms of vectors and matrices. And so maybe the strict answer to your question is you could do without them. You definitely would not want to. Life for mathematicians and quantum physicists and really anyone who works with like linear algebra and polynomials would just become incredibly awkward. So in some very real sense, they are a natural construct, so much so that even if you could do without them conceivably, you never would want to. It would really make things quite the pain. So coming back to our quiz here, it looks like, again, we've got a lot of strong consensus, which is good. And let me go ahead and grade this. All right, so the correct answer is A. Okay, it's root 2 over 2 plus root 2 over 2i. It looks like the majority of you got that. And okay, so very interesting is that the second most common answer was D, that no solution exists without extending beyond the complex numbers. Because the question we're asking in this context is basically to take a square root of I. So if you think of, oh, I is defined to be the square root of -1, I think a common question is to say, you know, how deep does this rabbit hole go? Okay, if we had to make up an answer to the question square root of -1, do we have to make up another one for the square root of I and the square root of that and just kind of keep extending and extending? And it's interesting and surprising that once you have I, you have pretty much everything else that you want, at least when it comes to solving anything that looks like a polynomial. Okay, so the answer here, there's two ways to think about it. One of them is the brute force way, and then one of them is the more elegant way. So the brute force way looks like this. You're reading through the multiple choices, and you just kind of try them out. And in this case, when you try out square root of 2 over 2 plus square root of 2 over 2 times I, and you square it, so we're going to multiply it by itself. I'm going to actually do this just to illustrate that it's possible and that it's not super fun. Taking root 2 times root 2 for that first real part is going to give us 2 divided by 2 times 2, so 2 over 4. The real part will also include the products of the imaginary parts because of that I squared. So we're going to have root 2 over 2 times root 2 over 2, which, like we just saw, oh, excuse me, that was supposed to be 2 over 4. You can tell I'm a little all over the place today, which, you know, just because sometimes complex numbers get me excited. Root 2 over 2 times root 2 over 2 is going to be another 2 over 4, but this time it's times I, so we're going to have a negative in there. Okay, that's going to be the full real part. And then the imaginary part is going to come from the cross terms, something where there was only one I included. So root 2 over 2i times root 2 over 2, it's the same product we're doing over and over, it's always 2 over 4. And then we're going to add root 2 over 2 times root 2 over 2i. So we're going to add the same thing, and I'm not writing the i's here because I'm going to factor it out. Okay? So the real part involves subtracting these, the imaginary part involves adding them, and indeed when we subtract them, that real part is 0, and when we add them, that imaginary part is 1. So we just get 0 plus I, or I. And okay, it works, but imagine that you looked at this question and it wasn't multiple choice, right? Someone asks you to find a square root of I. If the only option you have is this terrible brute forcing, it seems like a very painful process, right? To try every number, try squaring it. If this is what you have to do, but in an insane trial and error, it would seem like magic if someone just pulled that answer out of a hat. But if you're thinking about it geometrically, it's actually a pretty straightforward question to ask. Because what you're saying is, we want a number such that z squared is sitting where I is, right? It's sitting 1 unit above. Well, if we know that rotation corresponds to complex multiplication, right? That means what we want is a number that rotates by 45 degrees. Because if you have a number that rotates by 45 degrees, then when you multiply by it twice, that's the same as rotating 90 degrees, so it gets you up to I. All right. Well, what number is that? We could think of it in terms of sines and cosines if we want. You know, this is going to be cosine of 45 degrees. This vertical part is going to be the sine of 45 degrees. And it's root 2 over 2 for each of them. This is something we were working out just by looking at the isosceles right triangle. Each one of these is equal to root 2 over 2. So that's very fun. Simply by thinking of the geometry, you could pull out of your hat the fact that the square root of I, or I should say a square root of I, is root 2 over 2 plus root 2 over 2i. Another answer would have been what happens when you rotate not 45 degrees, but if you were to rotate 45 plus another 180 degrees. Okay, so 45 plus 180 actually gets us 225 degrees all the way around. That's another number where if you multiply by it twice, it'll have the effect of rotating you a grand total of 360 plus 90 degrees. It'll kind of rotate you all the way around and then an extra 90. So in the same way that most positive numbers have two square roots, square root of 25 is 5, but it's also negative 5, and in the same way that even negative numbers, like negative 1, has two square roots, not only is it I, but negative I also satisfies this property, that when you square it, you get negative 1. Even I itself has two square roots. And in general, everything, except for 0, has two square roots. 0 you might consider to have like a double root, but again, that's sort of a story for another time. So that's pretty magical. And now let me show you another bit of magic, okay? Something where, again, you can come at a question that seems like it's going to involve just insane trial and error, but if you're thinking about the geometry of it, you're able to come to a pretty meaningful answer relatively quickly. All right, what's our question here? The equation x cubed equals 1 has one real number solution, x equals 1. Makes sense? You cube 1, you get 1. Among the complex numbers, there are two more solutions. Which of the following is one of them? Okay, so this time it's actually asking us to cube some kind of complex number, or to verify that when you cube it, you're going to get 1. I'll give you some time to sort of think about that. And in the meantime, let me take a sip of water and then take a question from the audience. What do we have? You showed that in order to find the cosine of a sum of two angles, you can multiply two complex numbers. Does that mean that if I need the cosine of a subtraction of two angles, I need to divide two complex numbers? Wonderful question. Yes, it does mean that. And dividing by a complex number is actually the same as multiplying by 1. In the same way that dividing by 2 is the same as multiplying by 1/2. You basically say 2 has the action of stretching the number line by 2. 1/2 as a multiplier has the action of squishing everything down by a factor of 2. That's kind of the inverse action. When it comes to complex numbers, to divide by it, you ask, what's the inverse action? So an example here might be, let's pull up something here. Let's say I wanted to rotate, negative alpha. That's what I want to do. So I'm going to do like cosine of beta minus alpha or something like that. That number could be considered the inverse, the multiplicative inverse of what you get by rotating alpha the other way. So up here we have, I'm just going to write it as CIS for cosine plus I times the sine of alpha. The inverse number over here is CIS of negative alpha. Right? That number is 1 divided by this. I could even write it out over here to say CIS, the number that's alpha the way along a unit circle, is equal to 1 divided by CIS of negative alpha. And vice versa. If I took 1 divided by CIS of alpha, this is equal to CIS of negative alpha. Now everyone who knows Euler's formula is kind of screaming at me that there's an easy way to see this in terms of exponentials, which is of course where we're getting with this. But because it's weird, this connection between complex numbers and exponentials, I don't want to just throw that down right away. I do want to emphasize that this should all make sense before anything like Euler's formula enters the picture. If you think of CIS as being basically a function to ask where do you end up if you walk alpha units around the unit circle in the complex plane, it's the number that you can use for rotating things by alpha degrees, so dividing by it will also get you rotating the other way. But the overall answer there is that division is the same as multiplication. So that's absolutely the right instinct. You could derive for yourself the angled, what would you call them? The trigonometric difference formulas if you wanted to. Great, so I think that's probably enough time if we punch back to our quiz, and let's tone down the pause and ponder music here. It seems like answers have sort of stopped rolling in, so this is as good a time as any to grade things. So the correct answer here, of the 4 options that we were given, ends up being, drum roll please, -1/2 plus the root 3 over 2 times I. Now, I just want you to imagine for a moment that if you didn't know any of the geometry of complex numbers, someone asks you this question, and if you were to able to spit it back decently quickly, it makes you look like a machine, right? Because you would imagine that the only way to answer this is to look at each number and then cube it. That you have to go through and do the whole first, inside, outside, last, but twice because you're cubing it for each one of those, and then deduce that answer B turns out to have this property that we want. Geometrically, there's a very nice way to see it. So let's go ahead and pull it up. What we want is an action so that when you do it 3 times, you end up back at the back at 1, basically. If I were to multiply by this number 3 times, I end up back at 1. Let me clear for myself a nice new piece of paper here. So just remind ourselves what we're looking for, which is x cubed is equal to 1. Okay, so one such action is the do nothing action, right? If you multiply by 1, which does nothing, yeah, do that 3 times, you end up back at 1. That is our real solution. The other ones would be to rotate 1/3 of the way around the circle, okay? To rotate 120 degrees. Or you could rotate 120 degrees the other way, which is equivalent to thinking of rotating 240 degrees around. Those are other actions where if you do them 3 times, it's the same as doing nothing. If I rotate 120 degrees, then do that 3 times, I cube it, that's the same as doing nothing. That's how you can read this equation, which I think is very nice and elegant rather than just trying to plug in numbers and see what comes out. So using the trig that we learned about last time, this again comes from a 30, 60, 90 triangle. You can see that the real part is -1/2, and then the imaginary part is the square root of 3 over 2. So even before working it out, I can know with confidence that if I were to go through the painstaking process of taking -1/2 plus the square root of 3 over 2 and cubing that, I'm going to get back 1. I don't have to go through that process to know that that's going to happen, which is pretty magical. This also answers for us a mystery that we had in the last lecture. If you guys remember, what we did is we pulled up Desmos. So let's go on back. Let's go on over to Chrome. Let's open up a Desmos tab. And let's get rid of whatever else was going on in here. And what we played with was the idea that if you take a cosine graph, and then if you square it, the shapes look remarkably similar. You have this bizarre relationship where squaring cosine looks like squishing it. And more specifically, we were able to play around and say, if you double the frequency of that cosine wave, and then you manipulate it in some other ways, we're going to shift it up, and then we divide it by 2. This is all something we did last time. We got an identity between them. But this raised an interesting question. What on earth does cosine of 2x have to do with cosine of x squared? Well, now with complex numbers, we can actually know the answer. We can work this out. We know that if you rotate around by theta degrees, okay, if we call that number z, then when we rotate around another theta degrees, this new number is z squared, right? And z is what I was calling cis of theta, which we could expand out as saying cosine of theta plus I sine of theta. And we can work out that square merely algebraically. We take cosine of theta plus I sine of theta. The real part of that is going to come from 2 products of the real part. So it's going to be cosine squared of theta. But then also 2 parts of the imaginary. And because of that I, it becomes -1. So we'll end up with negative sine squared of theta. And then the imaginary part is going to come from, I might as well just write this out in full. Cosine theta plus I sine. I realize I'm kind of running against the edge, which is why I was hesitant to do this. But basically that cosine squared comes from taking the cosine times the cosine. The negative sine squared comes from taking I sine times negative I sine. Our remaining terms are going to be that cosine plus I sine. So cosine theta times sine of theta. And then there's going to be an I. I'll just write it out, times I. And then we get exactly the same thing. Sine of theta times cosine of theta times I. So sine of theta times cosine of theta times I. which we could factor out. This whole last part ends up just being 2 times the cosine of theta times the sine of theta. All right. All of that times I. So what we've done here is basically said there's 2 ways to think about cosine theta plus I sine theta squared. One of them is, oh, of course it doubles the angle, right? So that's going to be cosine of 2 theta. On the other hand, algebraically, it's equal to, deep breath, cosine squared theta minus sine squared theta plus 2 cosine theta sine theta I. Now that might seem like a big pain, but the big pain is showing us an identity. It's showing us the double angle identity. So what we found here, just to summarize on the real part, is that the cosine of 2 theta, the real part of what happens when we rotate by that twice, is equal to cosine squared of theta minus sine squared of theta. Now from another trig identity that we were working with last time, sine squared of theta is actually the same as taking 1 minus cosine squared. This was the alternate way of expressing the Pythagorean theorem. So we can get everything written in terms of cosines. And what we have is now 2 times cosine, pardon the messiness of the handwriting here, by the way, 2 times cosine of theta, all minus 1. That is evidently equal to the cosine of 2 theta. And we could rearrange that further and see what we were playing around with in Desmos, that this cosine of 2x expression, over here, this cosine of 2x expression corresponds with squaring the cosine. This was a reflection of the fact that cosine relates to complex numbers, which I think is pretty cool. Okay? And as the very last thing that I want to mention, I want to talk about why we didn't, why nobody really uses the CIS notation. Right? I was saying that CIS of alpha is not really standard notation when we're talking about rotating alpha around the unit circle. And as a reminder, this was my shorthand for cosine plus I sine. The reason is because what you're always going to see instead, through electrical engineering, through quantum mechanics, through math, through all sorts of things, is instead the way that this is written is, actually before I show you how it's written, no, I'll just show you how it's written. It's weird, and we're going to talk about it at length next time. But you imagine that you're raising something to a power, okay? E to the I times alpha. Now this obviously makes a lot of people very uncomfortable. First of all, if you don't know about E, what is E? And then secondly, what on earth does it mean to raise something to an imaginary power? So that is a full lecture's worth of material. I do want to talk about it next time. But just to give an indication of why this might not be a totally crazy thing, okay? I want you to remember the core property that we wrote down earlier, that when you rotate alpha around the unit circle, and then when you rotate another beta around the unit circle, this is the same thing as alpha plus beta. Which means our CIS function has this kind of interesting property, that adding the inputs is the same as multiplying the outputs. So with that, I want to ask one final quiz question, to try to relate this to other functions that you might be familiar with. And at this point, it might be halfway obvious where we're going with this. But as the very final question to cue you up for where we're going to go next time, and maybe appreciate the relationship at play here and why it's not that crazy, I want you to answer which of the following functions satisfies f of a plus b is equal to f of a times f of b. Okay. I'm being told, by the way, that when I advance the questions too quickly, it kind of reveals the answer of the next one, which happened all throughout last lecture, and you guys certainly told me about it. Again, this is one of those things where, like, this is what happens with live production. We thought we had fixed that. Usually, you know, this is a very weird process for me, because usually when I make videos, you catch some kind of error, so you edit out the error, then you put out the video. This as an experience for me is much more like, all right, world, here it is raw, here are the errors as they come. I hope you enjoy watching them happen, because there's no editing. It does not get clipped out. This is math presentation raw. All right, so as we do this, it looks like pretty strong consensus. I'll give you a little bit more time to submit the answers. All right, and with that, let's go ahead and take a look. So the question is, what function has this property where adding the inputs looks like multiplying by the outputs? So 2,700 of you correctly answered that 2 to the x, an exponential function, behaves this way. Looks like the most common second answer was A, that logarithms, which makes sense. There's an identity in logarithms that looks very similar. It's basically the opposite. So if we were to write this out, I might say 2 to the A times 2 to the B is equal to 2 to the A plus B. And when we're thinking in terms of repeated multiplication, this makes a lot of sense, because one of these is saying multiply in A copies of 2, then multiply in B copies of 2, and the result should be, well, A plus B copies of 2. The rule with logarithms is exactly the opposite, and it's because logarithms are the inverse of multiplication. On that front, it looks like taking the log of A plus B ends up being the log of A the log of A times B, multiply log of A plus log of B. Logarithms is another thing I think we're going to talk about in a later lecture of this series, so if you don't know about them, don't worry. But to those of you who answered that, totally understandable. It's because it's a very similar property, but it's just getting mixed up whether the outputs are being added or the inputs are. Now, what you'll notice is, how strange. This factor that comes about because 2 to the x is defined as repeated multiplication looks very similar to the rule that we found for complex numbers that sit on the unit circle, that multiplying the outputs is the same as adding the inputs. And that should be very suggestive that there might be some kind of unifying theory between them, which of course there is. It has everything to do with why we write things as e to the I theta, which I actually think is kind of a bad convention. The good thing about it is that it does make it pretty obvious when you take e to the I theta times e to the I beta, e to the I alpha, that you're allowed to just add them. It really highlights that fact, which otherwise you kind of have to think through. But maybe that's a good thing, that you kind of have to think it through and you're not just blindly applying rules. But I'm going to talk all about that next time. We're going to dig deep into Euler's formula, a way that you can try to understand, what is this really saying? Like computationally, it's not talking about repeated multiplication. So what could you do if you were on a desert island with a bunch of paper to just work out by hand the fact that this is a reasonable expression? All of that is to come next time. So thank you for joining. Apologies for being mildly scattered throughout